Welcome students. So today we are going to design a beam. Let's see what the problem says. A cantilever beam of length 4.5 meters supports a dead load which includes a self weight of 18 kilonewton per meter and a live load of 12 kilonewton per meter. Assume a bearing length of 100 mm. Design the beam. So the length of the cantilever beam is given as 4.5 meter. Okay, and we have to calculate the factored load which is acting on the beam. So this length is given. How much is this? This is 4.5 meters. 4.5 meter. So what is the factored load that is acting on the beam? It is equal to partial safety factor into dead load plus live load. Dead load is given as 18 kilonewton per meter and a live load of 12 kilonewton per meter is given. So you add up these two loads and multiply it with the partial safety factor and we are getting it to be 45 kilonewton per meter, right? Kilonewton per meter. So based on this factored load, now we have to calculate the maximum bending moment acting on the beam. So whenever a UDL is acting on a beam, on a cantilever beam, what is the maximum bending moment? It is equal to W into L square by 2. What is W here? W is the total factored load, which is equal to 45 kilonewton. This is W, 45 kilonewton per meter, and L is given as 4.5 meter. So the maximum bending moment will occur at the support, which is equal to W into L square by 2. It is coming out to be 456 kilonewton meter, and maximum shear force, which is also occurring at the support, okay, at the fixed support, that is equal to the total load, which is W into L, right? So the maximum shear force is coming out as 202.5 kilonewton. Okay. Next, what we have to do, based on the maximum bending moment which we have calculated, we must find out the plastic section modulus that is required for the beam that is to be designed. Okay, so in order to calculate the plastic section modulus, we will take the help of the value or the formula for design bending strength of the beam, which is given in our IS 800/2007. So let's check what the formula is. Okay, so this is the formula for design bending strength of a beam which is in low shear. Okay, page number is 53 and clause number 8.2.1.2. I would always ask you to write down the clause and the page number of the codes from which we are taking all the formulas. So here it says that when the factored design shear force does not exceed 0.6 times VD, where VD is the design strength, shear strength of the cross section, the design bending strength should be calculated as this. Okay, so this is the first line here is talking about the comparison between the maximum shear force that is acting on the beam and a critical value. Okay, and a critical value which is given by 0.6 times VD, by which we check whether the beam is in high or in low or in low shear. So whenever the shear force is less than this value, 0.6 times design shear strength of cross section, then it is in low shear, and we are considering the design bending strength of a beam in low shear, and based on this formula we are rearranging the formula to find out the plastic section modulus. Okay, so let's see what this terms mean. So first we have beta B, which should be taken as 1 for plastic and for compact sections, or if it is a semi-compact section, it should be taken as a ratio of elastic section modulus by plastic section modulus, right? So for our case, since we don't know, we don't have the section in hand, what we will do, we will assume that the section is a plastic section. The beam section is which we will design is already a plastic section. So we are going to take the value of beta B as 1. Okay, then Fy is equal to yield stress of material. It is 250, Fe 250, please consider it to be Fe 250, and gamma M0 is partial safety factor. Okay, so partial safety factor is 1.1. So we will simply rearrange this formula. Let's see. So this was my original formula with beta B taken as 1 and Zp that is required is maximum bending moment divided by Fy by gamma M0. So we know all the values. Maximum bending moment is, we have calculated it here. It is 456 kilonewton meter. F by 250 by 1.1, it is coming out to be 2006.4 into 10 to the power 3 millimeter cube. Or if you convert the plastic section modulus in centimeter cube, then what is the value? The value will be divided by 10 to the power 3. So it is going to be 2006.4 centimeter cube. Okay, this is my plastic section modulus in centimeter cube. Now what you have to do is that you have to choose a section whose plastic section modulus is either equal to this value or greater than this value. And from where will you choose the section? You can choose the section from the handbook which is provided for steel, that is SP6, or from IS 800 2007 also you can choose the section. So let's see how to do it. Okay. Okay, I think I should clear the drawings. Right. So let's first go to the handbook. Okay. All right. So here in page number, what is the page number? Okay. If you have the handbook with you, go to page number 2, right? Now, see the table says, the table belongs to rolled steel beams. Okay. And an I-beam is, the figure of an I-beam is already shown at the top of the page. And all the dimensions of this I-beam is also marked, right? See the overall depth of the beam is marked as H. This is the flange and the flange width is marked as B. Okay. Now see the axis, this is the XX axis, right? And this is the YY axis. Okay. This is the overall depth of the beam which is given as small h, and the width of the flange is given as B. Clear? Now you have the roots here. Okay. See, this is the root which is the junction of the web and the flange is known as the root. It is a rounded region and the radius is marked as R1. Now the toe of the flange is also a rounded shape. If you look more closely, the toe of the flange is a rounded section whose radius is marked as R2. Clear? Then you have the web whose thickness is given as TW, and the flange thickness, the thickness of the flange is given as TF, right? So now you go to the columns. First column will give you the designation of the steel section which you are choosing. Then you have the weight, then the sectional area, then you have the depth of the section as H. Now see, suppose we are considering ISJB 225. For that, what is the section? For this section, that is ISJB 225, the depth of the section is how much? It is 225. So this number means that the overall depth of the section is 225 millimeters. Okay, in the next columns, we have the width of the flange, then the thickness of flange, web of the flange, moment of inertia about XX axis, about YY axis, the radius of gyration about X and Y axis. Then again, if you go to the next page, again the same sections are given, right? And more specifications, more material specifications or geometrical specifications are given, like the modulus of section about XX axis, YY axis, root radius, etc. Now, in the handbook, you won't be able to find the section modulus, the plastics section modulus or the elastic section modulus. For that, you have to go to the code, that is IS 800 2007. So I have just taken a picture of my IS 800 2007 where the specifications of different I sections are given. So we have, it is given in page number 138, and I have chosen a section ISLB 550, right? Please write it down. It is ISLB 550, or you note it. So where is the section? ISLB. So this is my section. Okay. I will just change the color of my pen. Okay. So this is the section that I have chosen here, right? This is the weight of the section, sectional area, this is the depth of the section, the flange width, this is the flange thickness, this is the thickness of web, right? Radius of gyration, these are not needed right now. Now you have the section modulus values. Section modulus, this is elastic section modulus, which we don't require. We require the plastic section modulus. Okay. See, the plastic section modulus value is how much? 2228.16. And what is our required plastic section modulus? It is 2006.3, I guess, centimeter cube. So we are going to choose a section such that the plastic section modulus of the chosen section is either equal or greater than our required value for safety. Okay, right? Because we have to, because the section which we are choosing has to support or has to resist the maximum bending moment or the maximum shear force which is occurring on the beam. Okay, so we are choosing this section ISLB, and what we are going to do is that we are going to write down all the dimensions and all the specifications, whichever is required for the further calculation of the beam design. So let's go back to the problem. So step 3 is my selection of the section. So I have chosen this section ISLB 550, whose plastic section modulus is 228.16 millimeter cube, and elastic section modulus is 1933.2 into 10 to the power, this is 3 millimeter cube. Okay, the root radius is required, which is 18 mm. This is given in SP6. And the overall depth is 550 mm. The thickness of the web is 9.9 mm. The flange width is 190 mm and the thickness of the flange is 50 mm. That's it. Next step, what you have to do is you have to check whether the section is plastic or compact or semi-compact or slender. Already I have provided a note on plastic sections, compact or semi-compact or slender sections. This section checking is necessary because if it is a slender section, then it will be very much susceptible to failure. Okay, so make sure that whenever you are choosing a section, an I section or whatever section during steel design, make sure that your section is not a slender section. Okay, so we will check now what is the section classification from where? From table 2 of page 18 of IS 800 to 2007. Let's go to the code now. We will go to page number 18. Page number 18 is far above. No. 16. That's it. We have page number. Oh no, this is not it. Table 2 of page 18. Right, this is table 2, page number 18. Okay, so how will you do the section classification? First, you have to consider the flange and you have to calculate some ratio and you have to compare it with these values. Okay, see, for class 1 it is plastic. Okay, for flange, so first let me let you know that the section which we have chosen is a rolled I section. So for flange, we will be taking this rolled section. Okay, see, the compression element or the outstanding element of compression flange. So our flanges are in compression and it is a rolled section. So we are going to take this value. Okay, this row, I should rather say, we will choose this row and we will calculate the B by TF value. So what is my B by TF value? The B by TF value. Okay, first we have to know what is B. B is nothing but BF by 2, that is width of the flange by 2. I think it is given somewhere here. Okay, students, the value of B is not given here, but I think you should, it is given somewhere. Okay, but the value of B is taken to be half of the total width of the flange. Please mark it or write it down. Okay, so B is equal to half the flange width, not thickness, half the flange width divided by TF. TF is the thickness of the flange. So half the flange width is 190 by 2 divided by 15, which is equal to 6.33. And see, this value should be less than 6.33. See, this value is coming less than 9.4 epsilon. Okay, what is epsilon? The value of epsilon for 250, Fe 250 should always come 1. See, the formula for epsilon is given as 250 divided by Fy to the power half, or root over of 250 by Fy. Okay, so if you divide 250 by Fy, then it is going to be coming as 1, and root over of 1 is 1, so the value of epsilon is 1. So 6.3 is less than 9.4 epsilon, right? So our section is undoubtedly plastic. Now, if the value is coming out to be greater than 9.4, suppose the value of B by TF, suppose the value of B by TF is coming out to be 9.6. So what section will it be? See, this value is lying in between 9.4 epsilon and 10.5 epsilon, so that my value is becoming less than 10.5 epsilon. I'm writing epsilon as E. So which means my section will become compact. But in this case, our B by TF value is coming out to be how much? 6 point something. Okay, suppose 6.7. So since 6.7 is lying or 6.7 is not exceeding this value 9.4 epsilon, hence our section is actually plastic section, right? Now this is the classification based on only the flange. Next we will consider the web. We also have to check the classification with respect to the web. So we have our steel section, which is symmetric, and since it is symmetric, the neutral axis of the beam section will be lying at the mid section. So see, for the web, neutral axis at mid depth, we will be considering this row. Okay, so since the neutral axis of our beam section is lying at the mid depth, we have to calculate the D by TW value, and we have to compare the D by TW value with these three numericals, or these three terms, that is 84 epsilon for plastic sections, 105 epsilon for compact sections, and 126 epsilon for semi-compact sections, right? So what is a D by TW value coming? So D by TW, now how to calculate D? You have to calculate D by subtracting twice TF and twice the root radius from the overall depth. Our overall depth is how much? 550. Here I have written it as capital D. Actually it is, I should be writing it as D by TW will be equal to H minus twice TF. TF is the thickness of the flange, minus twice R, where R is the root radius, this divided by the thickness of the web, that is TW. Okay, so what is my overall depth? It is 550. 550 minus twice into, now what is TF? TF is given as 15 mm minus 2 into radius, root radius. What is the root radius value? It is 18 mm, 2 into 18. Right, this divided by the thickness of the web. What is the thickness of the web? It is 9.9. Okay, so if you calculate it, it is coming out as 48.8, and this value is less than 84 epsilon. Okay, this value is less than, okay, neutral axis at mid depth for the web, this value is less than 84 epsilon. It is not lying between 84 epsilon or 105 epsilon. Hence, our section is going to be classified as a plastic section. So we have chosen a section which has come out to be a plastic section based on both the checkings of the flange as well as the web, right? So what were the steps? Let's recap all the steps that we have done. So first we were calculating the maximum bending moment and the maximum shear force. Then we, based on the maximum bending moment, we had calculated the plastic section modulus. Now, based on the value of plastic section modulus, we had chosen our section, which is ISLB 550. Okay, we had written down all the dimensions and the material or the geometrical specifications of this section using the handbook and the code, that is IS 800/2007. Next, what we did is classification of the section, which has come out to be a plastic section. In the next video, we will be calculating the design bending strength and the design shear strength and check whether the beam is in high shear or low shear.